So it's a lecture. This is our first lesson we're having in biology, and I'm going to do an introduction to yeah, biomolecules and cells. Then we'll start first by looking at compounds and molecules. All right. So if you have any questions, if you have um, if you want or if you need help in any assignments in A levels, mathematics, can also be business mathematics, there's no problem. Yeah, feel free to contact me on any of these lines on the screen. Then, all right, so let's quickly begin to that. Okay, so if you have any questions, feel free to interrupt me anytime and ask. All right, so let us first start by looking at an introduction to what compounds and molecules are. So first of all, we'll talk about what is known as an organism. So an organism just depends on various chemical elements and compounds and molecules. So what makes up an organism are simply the chemical elements and the compounds and different molecules. And then compounds are simply just compositions of two or more elements which are bonded together. Yeah, so an example of a compound that has been given here is H2O. So H2O is the chemical formula for water. This too should be a subscript. So it's supposed to be written in this form, H2O. So this is a chemical formula for, it's a molecular formula for water. Okay, so this is an example of a compound because we have two elements that have been bonded together. And so we have the elements of hydrogen, and then we also have the element of oxygen. Yeah. We have two elements that are bonded together. Then we also have sodium chloride. So sodium chloride is also one of the compounds that we can talk about. It's just an example of the compound. Right. So let's also look at what molecules are. So the substance consisting of a few atoms of the same element, these are called molecules. So for something to be called a molecule, it needs to have it can have maybe two or three components, or let me say the atoms. It can have two atoms, it can have three atoms, it can have four atoms, but as long as the atoms that have been bonded together are of the same element, we call that a molecule. So for instance, we have O2, O2. O2, this is oxygen. So we're calling this a molecule because we have two oxygen atoms that have been bonded together. Then we also have H2. This is hydrogen. So we have two hydrogen molecules, two hydrogen atoms that have been bonded together, that are bonding together, and hence we call them, hence we call the result as a molecule because this is a set of, this is a substance that contains two atoms of the same compound, or rather of the same element, not compound. Okay, so we also have the chemical bonds. So this is just an introduction to everything that we're going to look at in this lecture. So we also have chemical bond energies. Yeah, so we're going to discuss this as we move further. Okay, let me just say something. So these chemical bond energies, their main application or their importance is just in the maintenance of organisms, organization structure. So this is something that is a bit straightforward. I'll explain it further as we proceed. Okay, so the likelihood that an atom will form a chemical bond with another atom depends on the number of electrons in its outermost shell. So this outermost shell is also known as the valence shell. So for or for us, it's for an atom. Yeah, for an atom, if we say this atom has it has high affinity of other atoms, it means that it has a few number of electrons in its outermost shell. Yeah, so um, okay, no, let me not use the word few, but let me just say the affinity of this atom um, to bond with another atom is determined by the number of electrons in its valence shell. So the valence shell is simply just the outermost shell. So we're going to discuss this even in chemistry as we begin to look at the valence electrons and everything. And then an atom with a valence shell holding 8 electrons is chemically stable. So some of these atoms are the inert gases. You've seen inert gases in the periodic table. Yeah, so such atoms have 8 electrons in its outermost shell. In their valence shell, they have 8 electrons. Those atoms are not are said to be chemically stable, meaning they can't react with any substance unless in what is in altered conditions. Yeah, so if they try to maybe change something, yeah, in an environment, or if not in an environment, or if they just try to change maybe something in the if they try to change maybe the chemical composition of that gas, maybe that's when it can try to react with certain things. But they are um, they are not reactive as long as they have 8 electrons in their outermost shell, which means that it is unlikely to form chemical bonds with another or with other atoms. So, like we say the likelihood of any atom to form a bond with another atom is the number, or is determined by the number of electrons in its outermost shell or in its valence shell. So, if this, if any atom has the maximum number of electrons in its valence shell, or if it has a stable, um, should I say, if it's chemically stable, it cannot react with another atom. That's what that means. So this is one of the examples which have been given here. Neon. Neon, for example, has 8 electrons in its valence shell. And for this reason, it does not bond easily with other atoms. Yeah, so neon is just one of the examples that have been given here. Yeah, so it has 8 electrons. It's also an inert gas. Yeah, it has 8 electrons in its outermost shell. Hence, it cannot react with um, other electrons. Okay, so let's quickly move on. So the atoms of most biologically important elements do not have 8 electrons in their valence shells. So this is self-explanatory. So the atoms of most of these compounds, or the elements um, that we use in biology, or these atoms that we use, that we mix with other, let me say, these elements that are mixed with other elements, or that are combined, or that are bonded with other elements to form elusive compounds, they usually do not have 8 elements in their outermost shell. So under the right conditions, 2 or more atoms can interact in ways that produce a chemically stable arrangement of 8 valence electrons for each atom. So this now brings about the types of bonding. Depending with the conditions, and depending with the types of atoms or elements that have been involved, or that are interacting, they can bond either ionically or covalently. Yeah, so they can bond either using ionic bonding or covalent bonding. Or if not that, there are also other very weak types of bonding, like the hydrogen bonding. We also have van der Waals We also have the types of van der Waals bonding, like the Lambda dispersion. We have different kinds of or different types of bonding, yeah, that we can discuss. I'm sure we're going to look at them. I think in the next slide in lecture 2. But in this one, I think we'll just end on covalent. Okay. So this chemical principle called the octet rule. So the octet rule is simply just states that for an atom to be stable, it needs to have a maximum of 8 electrons in its outermost shell or in its valence shell. Okay, so let's take a look at some types of bonding and how they are formed and their properties and even their importance in biology. Okay, so we have ionic bonding. We know that um, ionic bonding simply just involves an atom giving or gaining an electron in order to assume a stable status. So for an atom, when an atom loses or gains an electron in order to um, achieve its stability, that kind of bonding which is involved in the losing of an electron, there are atoms that have maybe only one electron in the outermost shell. Here they might have maybe 8 there. This is just a quick sketch. Let's say this is an original atom, then you have a nucleus there. Then you have another atom. This one has 1 electron in its outermost shell. Then this one has 7 electrons in its outermost shell. So what will happen is that this one with 1, for it to be stable, it's going to lose 1 to this one so that this one gains it and becomes stable as well. So this type of bonding is known as ionic bonding, where one atom or one element um, loses an electron and the other one gains in order to become stable and achieve or assume a stable status, that is that of what is a noble gas. Right. So this is known as the octet rule, the tendency of an atom to attain the maximum number of uh, electrons in its outermost orbital. I think I explained this before we came to this page. Yeah, so the octet rule just describes, or it just talks about the atom having 8 electrons in its outermost shell as a way of it being stable. Okay, let's look at sodium as an example, sodium chloride. The formation of sodium chloride is ionic. How we have sodium, which has 1 electron in its outermost shell, and then we also have chlorine, which has 7 electrons in its outermost shell. We have the last shell there contains 7. For sodium, the last shell contains 1. And as a result, we find sodium losing 1 electron and giving it to what? To chlorine, so that both can be stable. And in the process, they find they bond using um, the type of bonding called an ionic bonding. And you can see that sodium has remained with uh, 8 electrons in its outermost shell, which has made it, or it has achieved, or it has attained the what is the octet state, or the stability, the stable state in short. Yeah, so even this one, chlorine, you can see that it has gained 1 more electron, and it now has 8 electrons in its outermost shell, meaning it's now stable according to the octet rule. Okay, so the force of attraction is called the ionic bond. It's also known as the electrostatic bond. So the ionic bond is also known as the electrostatic bond. Yeah, and this is just an attraction which happens between 2 electrons where there is the process of losing and gaining of electrons in order for them to become stable. Okay, so sodium, in this case, since it's a metal, it's called a cation since it loses. So any substance or any or atom that loses electrons in order to become stable is called a cation. And then the other one which gains electrons in order to become stable is called an anion. All right, so they bond together uh, via the force that is known as the electrostatic force. Yeah, so the force of attraction is called ionic bond or electrostatic bond. All right, so let's look at the properties of the ionic compounds. So the first one is that these are soluble in polar environments, that is in water. Yeah, so they are soluble in polar environments. So we're going to discuss the meaning of polar as we begin to talk about water. So in the next, I think in the next chapter, there's a part where we're going to discuss water in details. It's important um, to know some of the important things um, that okay, some of the important things about water in short. Yeah, so water is also one of the important things that we need to discuss in biology. Okay, so um, properties of ionic compounds. The first one is that it's soluble in polar environments like water. Yeah, so what I'm just trying to lay is a foundation of what we're going to start discussing. In as we proceed, we start looking at things in details, like the lipids, we look at the proteins in details, we look at a lot of things in details. So uh, it is these things that we are learning today that are going to lay a foundation of, about what we're going to be discussing as we proceed. Right. So it is, ionic compounds are soluble in polar environments. And then they are insoluble in non-polar environments like oil. So ionic compounds are not soluble in non-polar environments. Then they conduct electricity when dissolved in water. So just from this weight, when dissolved from water, you can also get something from this because we know to say these ionic compounds are mostly what? Soluble, rather, are mostly crystalline at um, room temperatures. So most of the ionic compounds are, they conduct electricity when they are dissolved in water. So an example I can give you is just this common salt. When you put it in water, when you dissolve it in water, it conducts electricity. Yeah. So um, the other thing is that they are crystalline in nature at room temperatures. So the same common salt I told you about, it's usually in crystal form at room temperature. Yeah, unless dissolved in water. Okay, they have high melting and boiling points. Yeah, this is true. I'll still give you the same example of salt, the same common salt that we normally use. Yeah, that's the bond in that salt is ionic. So when you try to put it directly, not in water, directly on fire, you see that it has high melting point because it will take long for it to melt. Yeah, and it requires a lot of heat for it to melt. And they also have high boiling point. Okay, so let us look at the biological significance of ionic bonds. So they are very important in biochemical processes such as the transmission of nerve impulses, which we are going to, I think, touch a bit, and then maintenance of protein structures. So this one is coming. We're going to discuss it in details. Yeah, the protein structures, we're going to have the discussions about this in details. Then apart from that, they are also important in the production of energy in cells. This is also going to be discussed when you start looking at the saccharides. So don't worry, most of these things, we're going to discuss them. This is just an introduction. That's why I'm not even putting notes under them. Okay, so let's look at covalent bonding. Yeah, so remember, ionic bonding we say it involves the share, the transfer of electrons from one atom to the other. But in this type of bonding, which is covalent, the electrons will not be transferred from one element or from one atom to another, but there will be a sharing. They will be sharing electrons in short. So it is from the same sharing that the bond comes about. And then there are three types of covalent bonding. We have a single bond, like that one which is found in hydrogen. We also have a double bond, like that one which is found in oxygen. And then we also have a triple bond, like that one which is found in nitrogen. So let's look at these bonds. Yeah, so as I said, it involves two or more atoms sharing electrons in order to attain stability, which is the octet rule. So you have two or more electrons, rather atoms sharing electrons in order to attain stability. Yeah, which is the octet rule, meaning the atoms that are being involved in this type of bonding are not stable. Whenever you have a stable atom, remember what I said, any atom that is stable or that has 8 electrons in its atom shell or in its valence shell is said to be stable and hence is not reactive. They are not chemically reactive. Such elements are not chemically reactive, or such atoms are not chemically reactive. Okay, so this type of bonding, of covalent bonding I talked about was a single bond. Like, give an example of hydrogen. So in hydrogen, you find a single bond. Yeah, so you find a single bond in hydrogen, and this is an example, or this is a structure that shows the bond. So you can see that there's only one bond there. You see that we have one hydrogen has one electron in its outermost shell. The other one also has another electron in its outermost shell. So here there will be nothing like one electron moves from this atom to the other, because imagine if this electron moves, it means that this one will remain with no electrons. Hence, that will not even make sense. So what happens is that these two electrons, these two atoms will just share electrons so that they can both have two electrons in their outermost shells. What is happening here? You can see there's a sharing there that is happening. Yeah, and then the molecular formula for hydrogen is H2, implying that it has two elements of hydrogen, or two atoms of hydrogen. Okay, so let's quickly move on to a double bond, or a double and triple bond. So let's look at this. So we have the double bond, like that one which is found in what? In oxygen. So oxygen, as you can see, oxygen has 6 electrons in its outermost shell. So let's count. We have 1, 2, 3, 4, 5, 6 for this oxygen atom, for this one, this side. And then even this side, if you count the green ones, there are also 6 in the outermost shell. So for oxygen to become stable, it has to bond with another oxygen atom. And then these two oxygen atoms will share electrons. And then in total, the shared electrons will be what? Will be 4. And hence making each atom to be stable. And in the process of doing this, they attract each other and form a bond. Yeah, so this is the double bond that you are seeing there. So this is the structural formula for oxygen. And then this is the molecular formula for oxygen, showing that oxygen has 2 atoms in its molecular state. So whenever you hear a question in chemistry or anywhere else, if they say a molecule of oxygen, once you just hear this, a molecule of oxygen, just know that when finding the mass, the molar mass, you have to consider 2 atoms of oxygen, of oxygen. But if they say an atom of oxygen, meaning when finding the molecular mass or anything that you've been told to find, you are going to consider one oxygen atom. But if they say a molecule of oxygen, as long as there's this molecule name, you have to make sure that you consider two atoms when finding anything for that, in that question, as long as there's oxygen. All right, so let's proceed. Okay, so let's look at the triple bond, like the example which I gave here, which is the one for nitrogen. So as we can see, nitrogen here is sharing each is contributing 3 electrons, and then they share them together to make 6, because each of these atoms have 5 electrons in their outermost shell. So we can see that they bond by sharing 6 electrons. Yeah. As a result, they form a triple bond. Yeah. So as you can see, this is also a molecule of nitrogen, and then this is a structure formula for nitrogen. Okay. All right. So this is the end of tonight's session. It was a short session. So next time when we meet, we're going to look at the application and the importance, rather the significance of covalent bonding in biochemical processes. And then apart from that, we also have to discuss the van der Waals. Okay, let me just put up what I'm talking about. So we'll look at first the non-polar covalent bonding, also look at the polar covalent bonding. Then apart from that, we look at the properties of covalent bonding. Then from there, we'll discuss the biological significance of covalent bonding. Then apart from that, we'll also discuss the hydrogen bonds. Then also look at the properties of hydrogen bonds. Then we'll look at the biological significance of hydrogen bonds. Then apart from that, we'll also have to discuss the van der Waals bonds, then the types of van der Waals bonds. That's why we're going to look at the London dispersion and other types of van der Waals bonds. And then apart from that, we'll also look at the properties of van der Waals bonding. And then we'll look at the biological significance of van der Waals bonding. And that's the end of this chapter 1. And then from there, we'll proceed with other things. We'll look at water, we'll look at other things that matter. We'll also proceed and come and look at proteins, lipids. We'll look at a lot of things, not until we reach genetics. All right, so this is the end of tonight's lesson. So if you have any questions, if you have anything that you want to discuss with me, yeah, feel free to contact me on any of these lines on the screen. See you in the next lesson. My name is Hamted. Shalom.